Good afternoon, everyone, and thank you for joining our next installment of the Safer Sim webinar series. My name is Jacob Hayden, and I'm a program coordinator with Safer Sim at the University of Iowa. Safer Sim, or Safety Research Using Simulation, is a Tier 1 university transportation center with a research priority of promoting safety, and our webinar series features the research that is happening within our center. So thanks for joining us today. There will be time at the end of the presentation for questions and discussion. This is Zoom, so you will have access to a microphone or the chat box to type anything in if you do have questions or comments. And with that, today's presentation is a project from the University of Wisconsin-Madison. I'm pleased to welcome our presenter, Asher Elmquist.
Hi, thank you. So my name is Asher. I'm a PhD student at the University of Wisconsin. I'm going to present what we've been working on toward physics-based sensor models for simulating connected and autonomous vehicles. So I just first want to acknowledge SaferSim funding and the co-PIs on this project, Dan Negrut and Radu Serban. And then I want to give some context and motivation for this project, and that is kind of for simulation of automated vehicles in general. And what we're trying to do is provide training and evaluation framework for software, hardware, or human-in-the-loop simulation. And the reason to do this is to be able to simulate edge cases that we might not want to be able to run on a physical vehicle. And one of the things that we've been including in this is the ability to include in simulation interaction between autonomous vehicles, so two autonomous vehicles or an autonomous vehicle and a conventional vehicle or human-driven vehicle. And this diagram kind of shows what simulation of an automated vehicle in the loop would need to look like. So on the left here is all the sensor information, and that's what an AV would actually need to be able to see the world around it and localize itself in that world. And so we would then want to replace the physical sensors with simulated versions. And then of course that AV outputs a set of controls to navigate in the form of steering, braking, and throttle. And so as part of this simulation, we want to be able to take those controls and apply them to a dynamic model of the vehicle. And so in this way, we have a closed loop that includes the perception, control, and navigation of the AV. And so when I mention edge cases, this image on the top right is an example of one of those, right? So particularly safety critical scenarios where we might anticipate potential harm to a rider or damage to a vehicle. And so a simulation framework, kind of like what I discussed, would mostly be for testing and evaluation of vehicles, particularly corner cases like rear-ending or rollovers, but also for training, like training perception potentially. And that is because with a simulation platform, you can generate large amounts of labeled data for training. And you can also test individual components of this pipeline. So for example, you could test perception in a simulation framework, perception being something like image segmentation, object detection, localization, or SLAM. And that's because in the simulation, we can test these edge cases, but we can also test various different parameters to a scenario, possibly different weather configurations, different vehicles on the road, different numbers of vehicles in the scenario, and so on. And a couple examples here. The left two are what's heavily used in perception in AVs. So the top left is data from a LiDAR. And this can basically be used for localization of a vehicle, but also for object detection. So if we're trying to detect pedestrians, we might want to simulate this first so that we have an idea that we can detect pedestrians at a certain success rate, so that before we try to put this in use. The bottom is, again, the same thing, but for a camera. One of the issues that AVs, or particularly training perception for AVs, is that if you just run in reality, you can get kind of biases in the data that you use for training. One of those biases can actually just be children, because you don't see often as many children as you do adults, so you could actually end up accidentally biasing your perception algorithm toward detecting adults at a higher success rate than children. And then the image on the right is from a tragic accident a couple of years ago, where a perception algorithm actually failed to detect a pedestrian because it was not a common occurrence in training. And so it was unable to figure out if this was a pedestrian or a bicyclist, and therefore unable to accurately project where this person was going to go. So this is a prime example of the type of thing we want to be able to do in simulation. But in order to do this, we need to simulate the sensor data. Particularly if you look on the right, it's not a very crisp image. So we need to be able to simulate data that looks like this, that is as hard to detect pedestrians or any other objects as it would be in reality. But before I get into the sensor specific side, I want to talk about the framework in which we're developing this sensor simulation. And that's a project called Chrono. And it is a library, so it's middleware, so it can be embedded in a different application. And the reason for this is that we don't want to drive the software framework. We want to be a part of a software framework. And it's cross-platform, C++. And basically, up until this point, Chrono had been focused on vehicle dynamics or rigid body dynamics, flexible bodies, fluid-solid interaction, and dynamics in general. So the types of things that we can do, vehicles driving over deformable terrain or on-road. It's essentially a physics-based simulation engine, open source and free to use and free to redistribute and include in software projects. There's a couple of websites here if you want to have a look further. The bottom left is kind of an illustration of how we go about simulating the suspension of a vehicle. And so we're trying to build up this vehicle so that the dynamics of the vehicle match the dynamics of the real vehicle. And the reason that it's important is particularly if you look at edge cases that involve dynamics like snow or rain, we need to be able to, in simulation, mimic the constraints of the vehicle. So if the algorithm decides, hey, we need to slam on the brakes because there's someone in front of us, we need to then accurately simulate how long it takes for that vehicle to stop. The image on the right is a vehicle on deformable terrain. It's just an example of what can be done in Chrono. And I don't want to get too far into the software organization, but just to understand where the sensing development comes in, is that we, as a lab, one of the things that we're interested in is high performance computing, so making the simulation efficient. And so we build this dynamics engine on top of specific hardware platforms. And then we endow this physics engine with certain capabilities from a simulation perspective. So there's a finite element component, a fluid solid component. So for example, if we want to understand how vehicle mobility works and we want to drive a vehicle through a ditch full of water, we can simulate that. And this is kind of the level which we want to include sensing. So we want it as a fundamental capability inside Chrono. And then of course there's some external API to that so that a user can easily set up scenarios. And that's just the context. I don't want to get too hung up on these details though. So then diving more into what we've been working on for this project, which is the sensor side of things. The sensors that we support now are a camera, so an RGB camera, time-of-flight LiDARs, specifically time-of-flight scanning LiDARs, which is what is most commonly used in automated vehicles. So, for example, the Velodyne LiDARs are scanning LiDARs. Then also GPS and IMU. For the visual sensing, which is camera and LiDAR, we are leveraging a ray tracing library called Optics. And the reason for this is that because then we're using ray tracing, we can mimic the physics-based acquisition of light for those sensors. From a implementation perspective, we want to make this as efficient as possible. So the bottom diagram just shows that we can kind of simulate the sensing at the same time we simulate dynamics. And we can also then account for the lag between when a camera takes an image and when that image comes back to the automated vehicle for control. And the reason that that's important is that if we just said that the image came back instantaneously, we could get overly optimistic results saying that this vehicle can, detect pedestrians and then react instantaneously, when that's not the reality of sensing. Additionally, since I said we wanted to be able to support multiple autonomous vehicles or multiple autonomous vehicles and human-driven vehicles, one of the things that we focused on is being able to scale this environment up. So we can kind of scale this to larger compute resources, so multiple GPUs, multiple devices on the same computer. We've also, as part of a slightly parallel project, we can do this across multiple computers as well. So then I'm going to quickly dive into what we can support when modeling all four of these sensors. And the examples I'm going to show for these sensors are really just examples. I'm not trying to show validation. I'm just trying to give you a sense of what these types of distortions or artifacts actually look like. So for camera, we support a ray tracing method, but importantly, we include certain distortions, artifacts, and noise. And the importance here is that if we don't do this, an autonomous vehicle in simulation gets an overly optimistic look on the world. So it kind of gets the ground truth of the world around it, when in reality, a vehicle on the road might have a difficult time seeing things in the fog or the rain, or it might have a lot of noise on the sensor that might make it more difficult to detect certain things. And so some of these are lens distortion. So that's the example I'm showing on the right. And that's for when you have a wide angle, particularly when you have a wide angle lens, the image becomes distorted. And while you can correct that, it just fundamentally changes what your camera can even see. And we also include image noise, motion blur, and lag. So the example I have here for image noise is one that is based on the acquisition process of a camera, and that is a Gaussian model that is dependent on the pixel intensity. So how bright the pixel is will also determine how much noise that pixel experiences. So on the right here, I have a simulated image and a real image, and hopefully you can see this if the resolution is high enough, but you can see the quality of the noise on these images. And again, I'm not trying to show that this is validation. That is part of further work that I'll discuss at the end a little bit. But you can see the type of noise that we add to these images. On the LiDAR side, this is one of the more, along with camera, probably the most popular or common sensor for perception on autonomous vehicles. And again, we use a ray tracing method because this fundamentally mimics how a LiDAR operates. And by doing this, we can discretely model the beam so that we can incorporate what happens when the beam diverges and actually reflects off multiple objects. We can also include what basically amounts to motion blur, and that's the scanning artifacts that are induced when a LiDAR spins. And then we also include lag and noise. So that the scanning artifacts is because a LiDAR often spins somewhere in the range of 20 hertz. And for a vehicle moving potentially quite rapidly, by the time that LiDAR actually gets all the way around, you could have moved a significant distance, or objects around could have moved a significant distance. And so here's a concrete example I have of that. So this is in simulation, a LiDAR moving at 20 meters per second, kind of through a hallway full of cylinders. And this is based on a Velodyne LiDAR that rotates at 20 hertz. And the lighter gray points are what the LiDAR would see if you include the time it takes to scan. And if you just assume the LiDAR scanned instantaneously, which is what some current models actually assume in simulation, then you get a very different picture of the world. And so this could potentially change where the vehicle thinks pedestrians are, or where it thinks other vehicles are. And so this is a very important aspect to try to model in simulation, because it's what matches reality. Also, another very important aspect of LiDAR, which is often simplified out in sensor models, is beam divergence. So actually, as the LiDAR pulse is emitted, it has some small but finite angle at which it diverges. And so the left here, you can kind of see an example of that, which is enlarged so that you can actually see what's happening. And so if you see the edge of potentially a wall here, some of the reflection will come off the first wall, and some will come off the back wall. What ends up happening is you see two objects. And so the LiDAR itself could actually detect either one. And for certain LiDARs that are really common in AVs, you can actually detect both. And so the way we do that is we send out multiple rays per beam in the LiDAR, and we can actually mimic this return and detect multiple objects. Here are two examples of what this data actually looks like in a virtual environment. And it's very complex data, but it's very feature rich, which is why it's used commonly for perception. Then moving to the GPS model. For this, we actually use the internal dynamic states of Chrono and the objects that the sensors are attached to figure out what the ground truth position of the sensor is. And then we can apply noise, lag, and we can actually filter the data to reduce some of the noise that can be in a simulation environment when you are using numerical integration methods. These are just examples of in simulation we drove kind of around a section of Madison near campus, just collecting data just to see if we could make sure that we were our virtual world matched from a spatial aspect to the real environment. For IMU, it's a similar thing. We look at the internal dynamic states for Chrono, and we use that as the ground truth, but then we distort that and add noise so that the AV would get synthetic data that is as difficult to interpret as the real data. And that includes noise, lag, and again, this filtering window. So here's an example in Chrono where we use the Chrono sensor, which is the sensing module, and Chrono vehicle, which is the vehicle dynamics module. And we have actually for this a human in the loop. So we have a student in the lab driving this vehicle, and we're collecting data from this virtual environment. Top left is a camera that's mounted on the hood. The top right is a LiDAR that's mounted on the roof. And so, you could place certain control strategies on this vehicle to understand how they perform. You could also drive it with a human like we did here and collect data, synthetic data that you could use afterward to evaluate new perception methods or train perception algorithms. This virtual environment here is just an example. It's something we were collaborating with a company called Continental Mapping to reconstruct a virtual environment from the real world. And so the low quality of the buildings is not something that's inherent to the simulation framework. It's just because of the assets we're using for this demonstration. Here's a couple of examples, getting to a little further from on-road, but just another examples of how we can use the sensing module. We could take it off-road. The top left is an example where we actually trained using reinforcement learning, trained a vehicle to navigate this environment. We could do a similar thing with an on-road experiment. The bottom one is when we actually trained a convoy, and you can see here there are some issues with the convoy's navigation, but the first vehicle is kind of leading a convoy, and the three behind have learned how to follow, which is why they don't do a perfect job navigating these obstacles. And the right is just a scenario where a scaled autonomous vehicle, so it's an autonomous vehicle that we're actually working on developing from an RC car to be able to compare simulation with reality in a couple of scenarios. So looking ahead, one of the things that we were trying to do is to validate these sensor models. And that goes beyond just comparing the synthetic data to the real data, and that's looking at the effect that our synthetic data has on downstream processes. Because that's ultimately what we care about is how does a segmentation network or perception in general perform on our synthetic data versus if that data was real, because we want that to be the same decision. Basically, we want the perception algorithm to make the same decision on our synthetic data as it would on real data collected in the same scenario. And one of the things that kind of goes along with that is this idea of data realism. So for a camera, we often talk about photorealism, and that's what looks real to a human. We're interested in what looks real to a perception algorithm. Because once we can achieve that, then we can start putting AVs through different sort of scenarios and understanding how they perform. And then we also want to expand our sensor support to a couple of other important and common sensors. And then based on some of that validation work I was talking about, we want to improve the realism so that what we can learn and study in simulation can get closer to reality. And the last one is kind of a follow-up to that video I showed. We want to be able to improve the quality of the virtual environment, because that goes hand in hand with improving realism. So just a couple of resources I want to have here for you. The code is publicly available if you want to have a look or you want to potentially use it. There's a Chrono tutorial if you're interested. There's a paper here kind of covering some more general methods and models when it comes to simulating AVs, specifically the sensors for AVs, if you're interested in that more. And then the Safer Sim project report, which covers this presentation in more detail. And then a couple more, and that's my emailing if you're looking for more information as well. So thank you.
Great, thanks, Asher. A lot of interesting stuff there. So we do have some time for questions or comments. I will open that up to our attendees. We are using Zoom, so you do have microphone access if interested. Like I said too, there is also a chat box.
Hi, Jacob. Hi, Asher. This is Chris from NADS.
Hi. Oh.
Thanks. Yeah, thanks for the great talk. So my question is, how do you deal with the overly simplistic and idealistic representations of the environment in simulation? In other words, everything is a polygon, right? And sometimes there are relatively few polygons to make a building or even a car or a pedestrian. So how does that affect the data realism of these sensor models? And
yes, sorry, go ahead, keep going.
And do you have a way to mitigate that or compensate for it? Thanks.
Yeah, so that's a really good question, because it definitely goes hand in hand, like you said, with realism. So we can have the some magically perfect sensor model, but if our virtual environment looks bad, we would expect the data to look bad. And let me try to go down here for an example, right? So we can see here that we might have a good sensor model, but even if we did, then we're inputting potentially low quality information. And so one of the things to mitigate that is to just create a better virtual environment like you would for graphics, for any sort of game development. And this is kind of an open research question in general, which is how do you generate these environments? Because the background data, what a camera sees in the background or what a LiDAR sees in the background, has a huge influence over what decisions these perception algorithms make. So I don't have the answer specifically to that, but the same techniques that we can use for game environment creation, we could potentially use for sensors, like vehicle simulations. And the same environment that's used for the camera is used for the LiDAR. So we can use graphics techniques like deformation maps or normal maps to try to include extra detail, even though the geometry might be simplified. And so we can kind of leverage some of those game and rendering techniques. But I ultimately don't have the perfect solution for you, unfortunately.
Thank you for the question, Chris, and thanks for the answer. And I think obviously there's more work to be done. I do want to mention that that this presentation will be available on the SaferSim YouTube channel by the end of the week, and we will send that out to all the registrants. So if you're here today, you'll likely get that link when it's available. We will also include that SaferSim final report link when we send it out, and I will check with Asher to see if there's any other links. I know there's a lot of he included a lot of links to the different products and videos that he has, so maybe there's other things that we can include that would be helpful. If so, we will do that. But with that, I think we are going to wrap it up for the day. Thanks again, for joining. Thanks, Asher, for the presentation, and we will keep you informed about our future webinars. So
thank you for having me.
Yep. Have a good one.
Thanks, Asher.
Thank you.